Next up, please welcome Simon Handler, who's here to speak to you about the Martian Ocean.
Before I actually start, can I just make a brief comment, Sylvie? You know, there's an assumption that's been made in this business with the neutrinos. The idea is that the neutrinos interact weakly with matter. But this assumption, the assumption that's being made here for this experiment, is that the neutrinos actually pass through solid rock with no interaction. Do you see my point? This is not comparing light in a vacuum with neutrinos in a vacuum. Supposing that in fact the neutrinos are weakly, but nevertheless interacting with the matter over that 723 kilometer long stretch of crust, which of course we don't know the details of what's in that crust. We know the general geology. All that apart, I don't want to trip over here, you may well be aware of NASA's very best kept secret, which is that we are in the middle of the year of the solar system. The year of the solar system was declared by NASA in October 2010. Hands up all those who are aware that we're in the middle of the year of the solar system.
You told us last time.
I know I told you last time. I think many of you have probably forgotten. Anyway, it actually continues until August 2012. Don't worry, these international years are never 12 months long. I think because it takes a wee while for people actually catch up with the fact that they're even taking place. Well, I decided that this would be a good opportunity to actually, for us at the RASC Ottawa Centre, to actually celebrate the year of the solar system. So I've actually got a number of talks on planetary geology in our solar system. I presented one 2 months ago about the incredible late shrinking moon. This time around, we got a different story. The story this time is Martian Ocean ? And this is yes, according to the deltas. Bear with me. So while NASA continues to chase its tail in search for water on present-day Mars. Oh, and by the way, did I just move the? Oh, that's what I was looking for. Yeah. Which one's center button? I don't want to change. That's just for the. There we go. That's what I want. Great, Chris. I'll ask you to change this per usual. Chasing its tail in the search for water on present-day Mars, planetary geologists have been arguing for decades about the possibility of an ancient ocean, northern ocean, on the red planet. Now, this debate started with the Mariner images of Mars from the 1970s. This is not a recent debate, when it became pretty obvious that the Martian land surface was divided into two principal terrains, as you can see. Oops, next slide, please, Chris. There we go. As you can see here, the southern highlands, here, all pockmarked and cratered, and then here, the northern plains, much smoother, far fewer impact craters. Now, the primary observation that the highlands are riddled with far more impact craters than the northern plains made it pretty clear, even in the 1970s, that the surface of much of the Martian northern hemisphere is significantly younger than that of the southern hemisphere. And the ensuing debate has focused on how to resurface the northern hemisphere after the formation of the old Martian crust, now preserved in the south. Now, there are two principal hypotheses which have captured most of the attention. The first is that the northern plains represent the equivalent of a giant lava-filled impact basin, similar to the Mare on our own moon, making it, if that were the case, the largest such impact in the solar system. The second hypothesis is that the northern plains represent a lava-covered floor of an ancient ocean. Now, a recent paper in the scientific magazine Nature Geoscience suggests that we can now support the existence of an ancient oceanic-sized body of standing water in the northern hemisphere, on the northern plains of Mars. So tonight what I want to do is take a look at that geoscientific evidence, and let me tell you from the outset, it's pretty good. But before we do, let's ask ourselves the question. Think about this. How do you identify an ocean on a dry planet? Next one, please, Chris. On Earth, it's pretty straightforward. An ocean is a body of standing salt water made up of local components that we refer to colloquially as seas. The way we delimit the ocean is even simpler still. We simply trace out its shoreline. Admittedly, the boundaries between oceans are a little more complicated, but for planetary purposes, we can simply state that the Earth has an ocean, and that's it. So what's the definition of a shoreline? And I mean globally. I don't mean where's the local beach at your favorite holiday resort. Keeping it simple, we can state that all ocean shorelines occur at sea level, making allowances for tidal and seasonal variations. But this really begs the question. We come now to the real problem at hand. How, on a dry planet, do we identify sea level? Well, it's easy when the planetary surface has ocean water present, as here. Next one, please, Chris. But how do we identify sea level if we take the water away? Don't be fooled by this image. What this shows you here, and these are garish reds and greens, those are the continents, and the blue here is our ocean floor. Don't be fooled by this image. Look at it through the eyes of interstellar aliens at some time in the distant future who are still trying to figure out if Earth ever had an ocean in its history, its earlier history. Suppose these aliens were highly skeptical. What would it take to prove to them that these blue lowlands, these blue lowland plains in this image, were once ocean basins? The traces of plate tectonics in the basins, such as the mid-ocean ridges you can see here and there, or the transform faults, which are difficult to see, but they're there in this image. There we go. You can see them quite nicely here, at a high angle to the mid-ocean ridge. Or the alternating symmetrical magnetic stripes, which are not present in this image. These tell you how the basin formed, but they don't tell you anything about the presence or absence of water. Enough water to fill those basins and turn them into real bona fide oceans. So what evidence do we need to actually convince the aliens? We need deltas. And by the way, for those of you that don't know, the way that our modern oceans form is by continents actually pulling apart. And then these large volcanic centers here in the middle, they actually are what create the ocean floor that we now see today. Next one, please, Chris. So what's so special about deltas, you might ask? Well, to answer that question, we have to look at what they are and how they form. So let's do this in 8 steps. Think Deltas Anonymous. My name is Simon Hanmer, and I'm a deltaholic. Step 1. Rivers flow, and some flow to the sea. Step 2. Rivers carry sediment, that's sand and mud to you, while they are flowing. Step 3. When river water reaches the sea or ocean, it hits but what is by definition a standing body of water. Step 4. From the river water's perspective, it just hit a wall. So it slows down and it stops. Step 5. As the river water loses speed, it loses its ability to carry the sediment and drops it on the sea floor immediately adjacent to the shoreline. Step 6. Because the river water is slowing down at the shoreline, the main river channel divides into a braided system of channels in order to evacuate the same volume of water in the same time as the water is headed downstream in the main river channel inland. Hence, the river system now has a delta shape whose pointy end points back up towards the river system. Step 7. When the braided river drops its sedimentary load, those sediments will also have a delta shape, which will survive even if you remove the water at some later stage. And finally, step 8. Rivers, by definition, tend to meander. They swing from side to side when they're flowing slowly, which means they change physical location. So it's no surprise to see that a real delta like the Mississippi has built up as a series of deltas that overlapped and piled up on top of each other in different locations over time. And the time we're talking about for the Mississippi Delta is about 10,000 years. Now, these 8 steps in delta formation lead to an obvious conclusion. Deltas, by definition, mark local sea level. And a series of deltas of about the same age will mark locations of the same sea level over a wider area. And because deltas are accumulations of riverborne sediments, they will mark sea level even in the absence of water, the water associated with their formation, including the sea or ocean that they've formed at the edge of. So I think you can see where we're going to go with this on Mars. But let's look at a couple of terrestrial deltas first. Next one, please, Chris. Here's the Nile Delta. There it is, nice and triangular. It's about as classic as it gets. It's located at the north end of the Nile River in Egypt, where the Nile River meets the shoreline of the Mediterranean Sea. Unlike the Mississippi Delta, which is made up of a series of smaller deltas of different ages, this is a single long-lived accumulation of sand and mud, and that's why it retains its classical delta shape. Next one, please. Now this is a false color image of the Lena Delta in Siberia at the north end of the Lena River. The different colors correspond to different sedimentary materials that make up the fan-shaped delta. Again, essentially sand or mud. And here you can readily see that over on this side, oh, there's the Lena River, by the way, going down that way. This side here of the delta, you can readily see the active braided streams that are confined to the east, while the isolated round lakes that you see over here, lakes and ponds to the west, they're located in an older, currently abandoned part of the delta. The point here is that deltas are not static. They're very dynamic things. They evolve through time. Next one, please, Chris. So now let's return to the Mississippi Delta in the southeastern US. And as you can see in this satellite image here, and the accompanying inset, so this corresponds to this. This delta does not have a simple fan shape. Next one, please, Chris. There we go. The easiest part to identify is the currently active delta. You can see how it looks like a bird's foot. That's actually the technical term for it. It is a bird's foot delta, surrounded by submarine sand, that's the yellow stuff here, which has been deposited by the river. Next one, please, Chris. Now, if we outline the successive components of the entire Mississippi Delta, there's the current area here, and the numbers here refer to the time at which these various components formed. You can see that the entire Mississippi Delta was built up over time, and we can see how it's a composite delta made of many fan-shaped components, and that the bird's foot is just the latest manifestation of delta construction. Okay, very nice. So what has all this got to do with the occurrence of ancient oceans on Mars? Well, the question really is, are there deltas on Mars, and can we identify them? Next one, please, Chris. And here, the answer is a resounding yes. The Earth version here on the right and the Martian version here on the left. So for good measure, what I've done here is I've juxtaposed the Indus River Delta in Pakistan with part of the delta from the Holden Northeast crater on Mars. And the Holden Northeast crater is located off the open end, the eastern open end of the Valle Marinaris, for those who know. Now notice how both have an overall fan-shaped structure, in which we can see the traces of multiple river channels. There's a really obvious one there, but look, there's all kinds of river channels over here. And here I think you can see the traces here of river channeling there too.
Simon, are they the same size?
Coming to that.
Oh, sorry.
Now, and in both cases, these were built by water flowing in from the left with respect to this image. In the Indus example, those channels are low standing and they're actually filled with water today. But in the Martian example, they're actually high-standing wiggly ridges made of consolidated sand and gravel that resisted wind erosion that has removed much of the mud that was laid down between the river channels. So what we've actually got here is the negative image of a delta, represented by ridges rather than channels. Now note the absence of scale bars, because these deltas are not the same size. The Martian one is much smaller, but that actually doesn't matter, because the important thing from our point of view is we want to establish here whether delta-forming processes have occurred on Mars, whatever the scale, and they clearly have. Next one, please, Chris. Now, this abstract-looking object is a perspective rendition of the complete Holden Northeast Delta, which is also known, if you ever come across this, as the Eberswald Delta. Why? I'm not quite sure, but it is. It turns out that only the northern part of the delta up here has a classic delta shape to it, or fan shape. The rest is more a series, here, 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 here. A series of bird's foot shapes, very reminiscent of the Mississippi Delta on Earth. And they probably built up through time. Next one, please, Chris. And here's another example of a Martian delta in Jezero crater. It's located just east of Syrtis Major, for those who know. And it's got a false color component here to highlight the different kinds of sediment. Again, sand and mud mostly. This is an intriguing combination of a classical fan-shaped delta, which you can see here, but it's been overprinted by channels going up through there and coming down through there, channels which have actually left bird's foot features. So again, a dynamic kind of delta, the kind of thing we've seen on Earth. Now, I've shown you these two Martian deltas because they're the ones for which I could find the best quality images. But, have you noticed? They both occur in craters. which means that they're deltas that formed along lake shores, not the shores of an ancient ocean. That's not a problem for us, though, because I wanted to use them to show you that delta-forming processes have occurred in Martian geological history. Next one, please, Chris. So here we change scale completely. This is a map of planet-scale distribution of Martian deltas, which was used by the authors of the Nature Geoscience paper. The red squares represent, that's these things here, there too, and then there. The red squares are interpreted to represent deltas interpreted to have formed at the margin of the Northern Plains Ocean. And altimeter measurements show them to sit at heights within a few hundred meters of each other, which by Earth standards is actually pretty good. Believe it or not, sea level on Earth doesn't occur at one level. It actually occurs within a range of altitudes. In other words, these things do indeed mark ancient sea level. They are actually of about the same age. The other symbols, the blue ones, they represent deltas which formed within craters. In other words, they're deltas that formed in lakes. Now, the fact that only 1/3 of the known deltas appear to be associated with the boundary of the Northern Plains might explain why the best images available on the internet right now from NASA are the images of deltas that formed within craters. Nonetheless, the red squares do appear to trace the boundary of the limit between the Southern Highlands and the Northern Plains, except around the northern part there of the Tharsis Plateau, or the Tharsis Uplift. I'll come to that in a second. Next image, please, Chris. That's an interesting observation, the lack of the deltas around the northern edge of the Tharsis Plateau there. And this is also showing up in this diagram, which is of the distribution of the density of river channels within the highlands, within the Southern Highlands. And the highest densities are indicated by the yellow and red colors. You can see them through here and over there. The northern limit of the channels represents rivers that did not necessarily form deltas, but reached the Northern Ocean and ended. Notice how the northern limit of the channels corresponds to the Southern Uplands, Southern Highlands, Northern Plains margin, except here, just north of the Tharsis Uplift. So this perturbation, if you will, in the distribution of deltas and river channels around Tharsis tells us that the highland-lowland boundary in this region here, is actually the result of the Tharsis Uplift itself. The fact that it's a plateau means there's been uplift. And that has then disturbed the boundary between uplands and the lowlands, rather than it being an undisturbed ocean shoreline. Next one, please, Chris. So, for the time being, it would appear that the Martian ocean hypothesis is once again in the ascendant. As Napoleon's mother said, pourvu que ça dure, which means, let's hope it lasts. Next one, please, Chris. And this is my final slide. But let's keep this likely Martian ocean in perspective. Earth is relatively large and endowed with sufficient water that 75% of the planet is covered by ocean. Mars itself is much smaller than Earth, and we're talking about a smaller ocean covering only about 1/3 of the planetary surface. More importantly, we know that ocean basins formed on Earth as continents split and drift apart in the global process known as plate tectonics. On Mars, we do not have a clue. I can't emphasize this too much. We do not have a clue as to how the northern plains might have formed as an ocean floor. And the issue is all the more complicated by preliminary observations that the material beneath the northern plains might be identical to the southern highlands, including impact cratered to the same degree, which would be the very antithesis of plate tectonics. In short, planetary scientists are making good progress in understanding the geological evolution of the Martian surface, but they've not got it all solved yet. Thanks for listening, and happy year of the solar system.